Everyone, and thank you for joining our webinar for today. My name is Ali Razak Klagi. I'm the product manager for material testing at Porosity. Today I'm joined with our concrete product manager, Guido Tronca.
Hello everyone. Thank you, Ali.
We also have Andre Naff, who is the head of our global marketing, as well as Serena Durangs, who is our online marketing specialist. They're working very hard in the background, making sure that our session is running smoothly today. And again, as I mentioned, if you have any technical problems, any difficulties with the video, with the audio, with the presentation, don't hesitate. Just contact them via Q&A chat box, and they should be able to help you and resolve the problem. So now that the formalities are out of the way, let's begin our session for today. Today's webinar is the second session to our Resistivity webinar series. Some of you might have joined us on Tuesday, or we kind of talked about the principle of resistivity, and we focused a little bit more on the sort of a lab-based sort of environment and testing. Today we're going to highlight surface resistivity as a tool for corrosion analysis and maintenance, mainly for the existing structures, and like an on-site testing. As you probably can imagine, corrosion of the reinforcing steel is the main cause of deterioration of any type of concrete structure. And being able to diagnose the likelihood and the rate of the corrosion gives a very good idea on evaluating the sort of expected life cycle of our concrete structure. Electrical resistivity techniques play a fundamental role globally for corrosion inspection, and appropriate tools that are required for the concrete repair are generally used over sort of a certain, like a long period, systematic period of time to provide such maintenance. In addition to that, cost benefits that come along with these tools, or like intelligently designed maintenance programs that come with them against your weight and repair approach, can be evaluated, and from there you can draw a solid conclusion of what to do and how to kind of get the best result out of it. And all of this, as long as you stay in parallel with the international standards and guidelines, for example, RILEM, and the literature that are available, you should kind of get your expected results and an evaluation that you really kind of need. On that basis, again, some of you might have already been with us for the Tuesday session. We're just going to go and talk about some theoretical background about resistivity, where it's kind of how it works, what's the actual principles, and where we can actually utilize it before we start our session. So electrical resistivity is actually a very powerful test principle, although it could be fairly simple. Corrosion of the reinforcing steel, as we highlighted earlier as well, it's one of the main causes or primary causes of deterioration in the concrete structure. In fact, the ability of the concrete, or the capability of the concrete, to provide almost like a physical and chemical protection to the steel is a key factor, and ultimately dictates the sort of a life cycle or lifespan of our structure. Guido has got a great example for you guys today, because this came from a little sort of casual discussion we were having on the chemical protection that concrete gives to reinforcing steel, which I'm sure is going to share with us later on. Electrical resistivity is related to the ability of the concrete in how it actually resists the access of these aggressive agents that would potentially lead into corrosion and lead into the failure. So again, concrete itself is not just the bed, but it's something to give the protection, necessary protection to the reinforcing steel. Now, the question that obviously we have here is that where do we find resistivity most applicable? In which areas for inspection? First thing that we can look at, Guido is going to break this down for us a little bit further, but we could basically break it down into categories. The new structure, when we do testing for durability, and in our case for today's session, existing structure where we're trying to inspect the likelihood and the rate of corrosion, for example. We can actually use resistivity, electrical resistivity testing for several different stages. We can use it to identify where we could potentially be facing corrosion. Based on the information, we'll define what repair work we need to kind of implement. And then after the repair work been carried out, we will evaluate and verify that the repair that has been done been effective, has taken care of the problem. But Guido is going to kind of break it down for us. Give us some real life examples of how these things actually kind of help us in general.
To go back to our preliminary discussion where we tried to find criteria to sort out all the different applications. I try to go back to the profile of the application that I personally did in my career, and mainly I would recognize two scenarios where either we have these new structures being built next road, and all the issues related to that are the checking of the specification. So basically you will work for the contractor in order to help him provide the required material, or you're working for the supervisor having to check the thing. This is what we tried to cover on the first session, while the other approach, the other scenario, the other customers were maintenance engineer or structural engineers dealing with an existing structure. You could know maybe everything about the details of the construction, or you might simply not know anything, but the problem was, hey, how is the structure today? How can I optimize my maintenance procedure? And if the repair is to be done, how can I save more money? So this is how we sorted out the application. And today, let's go outside. Let's go on actual existing structure with potential troubles with weathering.
You mentioned how we can save costs, and this was one of the main topics we highlighted again on Tuesday's session, the cost benefits of electrical resistivity. So for those of you who missed that session, it's going to be available on the YouTube. Again, my colleagues at Marketing, Serena, has been working on that already, so we should be able to upload that sometime very soon for you guys to go and have a bit of a recap, for example. Thanks, Guido. Now, moving on from there, Guido mentioned that how we can actually utilize electrical resistivity for on-site testing based on our application. So when it comes to the point that we decide, okay, we're going to go ahead and utilize electrical resistivity, we need to obviously take into account the main contributing factors that directly affect the electrical properties of our concrete. Number one would be water. Water content is just like the first thing that comes to mind. In fact, in order to get the test started and get data, you need to make sure that your concrete structure has been kind of is wet and has some moisture with it. Second thing is the salinity of the pore solution. We got some pictures for you over here, as you can see. Porosity is again very important, and the interconnection between your pores also are a contributing factor. One thing to highlight here, although today we're talking about the existing structure, electrical resistivity can actually be used, electrical resistivity test principle can be used to monitor the behavior of your concrete during this curing stage as well, because these conditions tend to change as your concrete starts to cure. So this is some sort of a little side note for you guys. Again, we covered this in more detail on the Tuesday session. Now, if we were to kind of categorize, I'm sure there will be more, but if we were to generalize the electrical resistivity, we can put them in two sides. First first method of testing is the surface resistivity test. When the current is actually applied in the outer probes, and the potential is measured and read between the inner probes, and based on the spacing between our probes, the resistivity is calculated. On the other side, we could have a bulk resistivity measurement where we look at the resistivity of the entire specimen. In this case, we got a cylinder when the current is applied between the two plates, and the potential is read between these two plates for the length of our specimen. And again, based on the formula that you see over there, the resistivity of the entire specimen is calculated. The modern instruments like Resipod enable you to do this automatically. So all you're required to do is to set the instrument to the appropriate setting via the software that comes with it, and you're pretty much good to go. It takes less than a minute. And by the way, today we have some demo for you, live demo. We show you one little application. Now, hopefully that gave us a bit of a background, especially for those that were not with us on Tuesday. We're going to start a main session today. Approximately, we should be about half an hour. During this session, you may have some questions. Please do not hesitate. Fire away. Send us your questions via Q&A box. We will receive it. Andre and Srena will keep an eye on every question as they are appropriate to that particular section or slide that we're talking about. They will feed it to us, and we'll answer them there and then while everything is relevant and fresh. In any other case, at the end of the session, we will go through every single one of your questions and make sure every one of them is answered for you. And if there's any supporting document is required, again, we will send it to you from our webinar email account that you've been contacted throughout the communication for this webinar series. So on that note, let's start our main session, which we're going to concentrate on corrosion analysis or on a reinforced concrete structure. Now, when it comes to reinforced concrete structure or any type of inspection maintenance that we need to kind of provide, verifying the presence of corrosion is a key factor. Corrosion, we said it earlier as well, corrosion of the reinforcing steel is the number one durability problem that we will have to deal with. Corrosion is actually an electrochemical process that requires flow of electrical current in order to proceed. So concrete is, in fact, very capable of providing an excellent protection to the steel and preventing it from corroding. Later on, Guido will break down the sort of beside the physical protection, the chemical protection that concrete provides to the steel because of its alkalinity. So we've got a little example for you here with this graph, as you can see, how the aggressive agents in parallel to chloride or carbon dioxide actually start to react with our structure, and the effect of this that could potentially lead to failure over time. So corrosion is not something that happens immediately. It's the cycle of it that happens over time that potentially would lead to failure. Guido is going to kind of break it down for us here, and it really kind of go through each step and potentially introduce some plans of how we can prevent this.
Sure. Well, this is basically to stress the importance of the prevention. The failure mechanism that will inevitably occur in a reinforced structure starts from a zero time where the steel is there in a fresh concrete and it's just happy to be there. Concrete will grant a physical protection, but not only. When I try to explain the mechanism of the protection, we may assume that it's not so different than what we look with in our delicious tomatoes under oil that we had together recently. And it's just oil will prevent totally the tomato from rotting. Mm-hmm. Just the same, concrete will make a perfect environment for the steel. Mm-hmm. Reason for that is the high cement content inside the concrete involves a very alkaline environment, and under those pH, the steel, the iron, will cover itself with a thin film of a very well adherent oxide, which will prevent further corrosion. So everything is fine until over time some aggressive agents, and we're speaking about carbon dioxide, something we cannot avoid having in the environment, will permeate through the cover and will destroy the natural ability to provide protection to the steel of the concrete. Well, keep in mind that at this point we still have seen no damage in the concrete. It's just, but it is not granted the protection to the steel anymore. Now, especially if other aggressive agents are present, such as chlorides, that corrosion will begin. And the fact that corrosion begins will involve an actual damage to the concrete. That's where cracking or spalling will occur, and then the aggressive agent will have more ease of access to the steel. So it's a sort of an accelerated exponential curve, which reminds us that when we see the damage, it's too late. Mm-hmm. That is the general criteria before going into chemical details.
So electrical resistivity, you'd say, becomes a systematic quality control tool for us to monitor the behavior of a structure over time.
Absolutely. Absolutely.
Fantastic. So, moving on from there, what Guido's pretty much saying here is that the number one contributing factor to our witness or the likelihood of corrosion actually happening is the environment that we're dealing with. This was like something that we actually highlighted at exposure classes in the presentation and on Tuesday as well. When we're looking with to identify the areas that we could have potentially have corrosion, we're trying to differentiate between our anode area and cathode area. Again, we're going to break it down for you in a little bit more detail later on. And what's historically one of the most traditional methods that's been used to do this is a half-cell potential, which we will look into and then see how resistivity can contribute and supplement that test principle by itself. Again, the example that Guido has on the tomatoes and the olive oil, and the protection that's given is again applies here. So as you can see, the cement content of the concrete is providing that alkalinity that protects the steel from corroding, in opposite to what carbon dioxide does to make it actually. It's because of its acidic sort of property. When it comes to assessing corrosion, we got our sort of NDT methods, which we're going to highlight here, and then we can have some direct methods. If you were to look at the NDT methods, one of the sort of the most commonly known NDT methods is the half-cell potential, is the Canning one. So what Canning does, it gives you an indication for the probability of active corrosion in the structure that you're trying to kind of inspect. Surface resistivity is also used to assess the concrete ability of allowing corrosion. Thirdly, one of the biggest contributing factors, obviously, corrosion happens in and around our reinforcing steel. So we need to know where these reinforcing steels are and what concrete cover, which ultimately is providing the protection to our steel, are we dealing with. Thirdly, we talked about the environment. One of the most important environmental factors is the temperature that we're dealing with, because temperature provides the correction to the measured electrical parameters. So that's again very, very important for us. So these are like maybe 4 NDT methods that we could use to identify the possibility of having corrosion. On the other side, we could have some direct testing methods in our arsenal. We could chloride content, for example. We define the amount of a specific aggressive agent that we're dealing with. We could do some carbonation depth tests. So we're in this picture, as you can see, on the surface we expect some carbonation because it's exposed. But on the sort of core of the concrete, as some of the surface you can see is purple, meaning that we have almost no carbonation whatsoever, and that reflects on the health of this particular concrete structure. Lastly, we could go through some sort of a visual inspection, so where we actually look and physically see whether we have problems, we have corrosion, and if that exists, so then we need to make the appropriate measures to deal with that. So before we go into that and look at the half-cell potentials again, what would you say, Guido? So we've got the NDT methods and we got the direct methods, right? That all supplement our half-cell measurement principle.
Sure.
They could be used together as combination as well to give us a much, much better idea, can't they?
I would say that they have to be used together.
Okay.
It's not a matter of being a fan of direct testing or a fan of NDT testing. Corrosion assessment is not really an easy task, and it's unavoidable to use the whole information which you can bring by direct and non-direct testing. Of course, direct, non-destructive testing has the great advantage of being able to provide a broad information of a huge area. And then the direct spot testing, cores, opening, visual inspection. Now we have a criteria to know where to use them and to extend the information that we get from direct observation to the whole area. So the key word is that you need to combine information of non-destructive testing and direct methods.
Fantastic. And then we would get somewhere like half-cell measurement principle, and then we can combine them together. In this case,
let's go in some details.
Some details on
one of the most important.
Most important one, absolutely. So when it comes to half-cell measurement, we are trying to identify the area, to differentiate between our cathode areas and anode areas. And as you can see on the graphs over here, where we see the largest sort of negative potential, that's potentially our problematic areas where we need to kind of investigate further. Originally, we can have single electrode, but we could, to cover a larger area, then we could have a four-wheeler. What I want Guido to kind of explain to us a little bit more is the main difference when it comes to a single electrode, a real electrode, and a four-wheeler. What are the advantages of these different principles?
Of course. Well, again, normally when we're dealing with corrosion assessment, we're dealing with wide areas, with broad areas, and we need to cover them quickly, at least if we want to make some money with the testing. The original device is the handheld rod electrodes, which can allow us to do spot measurement, but hey, if you're dealing with a bridge deck or pier, you need something more. So where we came up with at ProSec was the first and only wheel electrode, and we had the chance to estimate the difference in productivity, which is huge. Of course, it's all a matter of the grid that you want to have, but let's say that on a suggested grid 25 by 25 cm, with that four-wheel thing, you can count, once everything is set, some productivity of around 1,800 square meters per hour.
Wow.
Which is absolutely not reachable with traditional. So it's not a physical principle. The measurement is the same. It's just logistical and productivity issue that we have.
Fantastic. It is fairly significant. I mean, the productivity that you get out of it. Now, and there are obviously, like any other test principle, there are contributing factors that affect half cell potential. Obviously, one of the most important factors are the concrete cover thickness. Basically, the potential which can still be measured at the concrete surface becomes far more positive as the concrete cover increases. On the other side of the scale, electrical resistivity directly influences the half cell potential as well, where when we're dealing with low electrical resistivity, we kind of expect more of a negative potential, and the potential gradients becomes kind of flatter. And as in the areas when we expect like a higher resistivity, we seem to see steeper gradients. And in these cases, we have to be we have to understand that we need to kind of have a grid much finer to accommodate these higher resistivity areas. We're going to cover that for you, and we've got a nice graph which Guido is going to go break it down and explain to us why we need to make such measures. But just to give you an example of what difference cover can actually make to your reading. In this graph, as you can see over here, we're dealing with two corrosion hotspots, both indicating a negative potential. So when we do a cover reading over here, you can see that our half cell potential is measured at about minus 400 millivolts. But as we do the cover reading on the next area where the cover is obviously larger, you can see that your half cell potential is far less. So the half cell measurement has to be in parallel to your concrete cover. So again, what you're doing, you're comparing apple to apple, even when you kind of doing like your area, you're scanning your area in your grid. Moving on from here, we talked about the high resistivity and the low resistivity. We got two graphs for you here to kind of show you the difference and how you should actually be dealing with it. There's some guidelines and standards also available, how you lay your graphs, how you lay your map, and how you set up your grids. But Guido going to kind of break it down for us in more detail, and especially talk about some of the recommendations that helps us even further. And
again, the design of the testing campaign, which is the critical starting point. So again, in this phase, we're just optimizing the half cell potential grid. So my goal is to try to be as coarse as I can, because I will save time, and but I don't want to run the risk of miss a hotspot. There are, of course, some indicative recommended grids. Typical one in Europe is 25 by 25
centimeters.
Yeah, sure. And others might just say, just go larger and then go finer if you find some gradients. But the general concept is that I have to have an indication of how broad or how fine I have to say. Now, this is where I use my Resipod even prior to the half cell, because if I measure a higher resistivity, I will expect a shape of the potential curve similar to the one on the left, so a narrow funnel, and I really cannot afford going with a broad spacing. On the contrary, should I measure a low resistivity in my preliminary measurement, then I will know that I can afford going a little bit wider, because the shape of the funnel itself would be wider. So this is the first step where I would use resistivity for, as an indication for optimizing my half-cell potential testing campaign.
Fantastic. You mentioned there are sort of based on the European standard, the recommended grid size. Is there a recommendation for the cover as well? Just as a rough guide of what sort of cover we're dealing with?
Well, typical covers that optimize that measurement ranges from 15 to 25 mm on a realistic structure, just to give some examples. Sure.
Okay, fantastic. Thanks for that, Guido. So moving on from there, as we kind of dealing with our high and low resistivity areas, one thing that we need to always consider, and this we talked about effects of rebar and half cell. We specifically talked about effects of rebar in the previous presentation as well. So when it comes to doing surface resistivity tests, after locating our rebars and finding out about a cover, we need to know how to do the measurements. Best way is to make sure that the rebars are not directly beneath our probes and should not run in parallel to our resistivity probes as well. And as much as possible, we should try to measure diagonally to the rebars. I mean, based on the location of our rebars and the intensity of them, then we can start using either the 38 spacing probe, we got the 50 millimeter spacing probe. In addition, we have the geometric kit, which allows you to define your own spacing and then set the instrument to accommodate for the probe spacing in order to calculate your resistivity measurement correctly. So influence of the steel can be generally minimized by measuring perpendicular to the rebar. That's like the key sort of learning here. And all of this information is clearly shown and highlighted in the Resipod manual structure. So if you need additional information, please refer to that document. And lastly, just again as a side note, it will come, just bear in mind, whenever you're dealing with sort of covers above 30 millimeters, the effect of rebars becomes very, very small. So you could almost ignore them in them sort of cases. But you would say, number one priority when you do a resistivity test, get your rebar locator cover meter out and locate your rebar.
That is something unavoidable.
Okay.
Sure.
So number one rule, always know where your rebars are, locate them, and know what your cover is, because that's what dictates the health of your resistivity measurements. Now, in addition to the rebars, which are one of the main contributing factors, there are other elements as well that we need to take into account because they contribute to the health of our inspection. The probe spacing we've mentioned several times. So probe spacing should actually match our aggregate size. So in fact, probe spacing should be larger than the maximum aggregate size that we're dealing with. environmental temperature, we covered that earlier. That is actually one of the main factors contributing to our measurements. And as an example, when you look at the sort of reference values given for resistivity, you find that it's around 20 degrees Celsius, and that does reflect the lab environment that you kind of deal with. Again, this presentation here, we are making the assumption that we based it around on-site new structure testing. But generally speaking, temperature can reduce the resistivity by about 3%, and for saturated concrete, and about 5% for dry concrete. On the other side, higher moisture contents drastically lowers the resistivity, so you need to take that into account as well. And carbonated concrete has far higher resistivity than the concrete without carbonation. So again, it is important to increase the probe spacing to obtain much sort of stable results when it comes to such scenarios. We talked about our live demo. We're going to show you we've got a little sample here. Guido gonna go ahead and on site, and then do the measurement for you. We're going to record the data, and then we're going to come back. So we just send Guido on site as quick as possible.
Okay. We needed actually a real structure here, which we do not have. So let's be happy with this cube, which we might assume be a bridge deck or whatever. It was just a chance to take a closer look to our instrument. Well, especially on site, the use of spring-loaded probes allow us to adapt the measurement even to irregular surfaces. The idea, of course, is just to have a proper contact to the surface. And here's the reading we get. Let me freeze this measurement for a minute. And so here we see our actual value of resistivity, and on the top of the monitor, okay, we have an indication of the current that flows between the outer probe. We want to make sure that contacts are good. So here we have an indication of the top of the global scale of the current, which in this case is 200 microampere, and it could be a lower range for lower resistivity. For higher resistivity, we can go down to 50 microampere, and then we have an indication of the percentage of the scale of the electrical current that passes. So the measurement in itself is very simple, rather quick, and especially since we are actually out on site, maybe close to the sea, close to the water, we need an instrument really ready for harsh environment. This is robustly built, IP67. I'm checking a bridge, I drop it in the water, it will float, I can pick it up and go for the measurement. So let's say that I'll spend my days or weeks testing on site, and I will collect all this data. We collected, well, one data, which is very significant. Now, coming back.
Let's bring Guido back from the site, and then put him back in the office.
Back in the office again. Tough job testing here at my PC again.
That was quick.
That was a good one. That was a lucky one.
Yeah.
But now that's the tough part. What does the number mean?
This is what you were kind of dealing with, weren't we?
That's it. Okay. Now, a first approach is just going straight to your result, to your table of your resistivity. I'll just look at the resistivity in itself. That's where literature helps. And, well, is it rusting? Is it not? Here's the first criteria to assess the likelihood, which is very important. So technically speaking, for this one measuring point that we have an indication of a moderate risk of corrosion. Well, whenever we see something below 100, we normally say that, well, there is conductivity. So we need to keep our eyes open. So we just went to the moderate likelihood of corrosion. Same thing, well, let's say that this building is already old, there is already visible rust, something is already happening, then I can provide an estimate of how fast corrosion is going today. Well, today in that structure, we may assess that we have a low corrosion rate. Just keep in mind that these numbers, these methods, in order to have a real meaning, needs to have the robustness of a statistically significant measurement. So, but this is the first criteria that we adopt.
So potentially we can get an idea about both the likelihood of corrosion and the rate of corrosion that we're dealing with measure minutes based on your test. I mean, you just done a test, haven't you?
Sure did.
There we go. Great. Thanks for that, Guido. So moving on from there, all of these tests that we've introduced so far, along complemented and supplemented with the surface resistivity test, you can actually gain a lot more clear idea about what you can actually achieve with it. We've got over here a plot, as you can see, with our half cell potential, and we want to show you that the relationship and the correlation that you have between surface resistivity and your half cell potential. Again, you're going to break it down for us. We've highlighted different areas in there for you to see what's going on.
This is a typical response that you might have on your desk once you completed the testing campaign. A mapping on a certain grid of half cell potential and a mapping of the resistivity. Now, let's keep in mind that half cell potential is measuring the steel and resistivity is measuring the concrete. So we see that graph and we immediately notice that most of the measurement align on something like a straight line, which defines a first area where most of our attention will be. Very negative potential and low resistivity values. Well, that is our very likely to have corrosion in action, and the concrete is not able to provide the required protection. This is where I will go for my first visual inspection, and that is probably will be the first chipping plan that I will provide my customer. On the other side, we have other areas where we see passive potential, meaning around zero, and high resistivity values. Well, that is where the maintenance engineer or the contractor will probably save his money, because we can grant that those areas are safe, provided that some visual inspection confirm this statement. But then again, please note how the potential in itself may be around zero. Take a look at the yellow area. If I only had the potential data, well, those would be okay area for me. But if those values are accompanied by a low resistivity value, well, then we can safely state that those areas are at risk for the future. Those are easy statements that normally are understandable to a final user or manager of the structure. Well, this is just an idea of how combined information is optimal to provide a safe assessment on the structure.
Brilliant. Great, thank you. So on that note, combining all of these information together allows us to determine the appropriate repair and the maintenance work that we need to go over, that we need to combine our resistivity and half cell, so on and so forth. So as mentioned before, provided that we go through such maintenance and repair program, we still need to verify that the work that has been done has been effective and dealt with the problem to start up with. Other things that we can actually check along here, we can check the resistivity of the parent concrete and compare it to the site, to this existing structure that we're checking. And on the other side, the effectiveness of cathodic protection system depends on resistivity of the concrete. So we should be able to kind of map out the resistivity prior to installation. That allows the structure to be kind of divided into sort of separate zones where we kind of expect levels of current flow. The current flow is different current flow is required. On that basis, that brings us to the sort of end of our presentation today. Let's just conclude what we covered and hopefully some of the key learnings that we highlighted today. Surface resistivity testing is actually could be one of the fundamentals, together supplemented by the half cell, for the assessment and of the likelihood and the speed of corrosion that we could potentially be dealing with. Concrete structure can be assessed early enough with such techniques and such principles, and electrical resistivity is for sure one of the most appropriate tools and techniques for us, obviously here. If we can take into account the financial savings associated with electrical resistivity test, I'm sure we'll appreciate it. And again, these are proven facts. In Tuesday's webinar, we clearly highlighted the cost benefits of electrical resistivity. And lastly, the maintenance work that has to be kind of introduced for the reinforced structures, we need to identify within that system that we defined the likelihood of corrosion existence, and by doing so, we can for sure prolong the sort of a life expectancy of a concrete structure. So again, using half cell potential and electrical resistivity techniques in parallel to each other, we will be able to get a great idea about the life cycle and what's the expected life cycle of our existing structure. On that note, I would like to thank everyone for joining us in this webinar today. We've actually conducted 4 webinars altogether. It was very exciting for us. And what we're going to do, we're going to start taking questions. There are quite a lot of questions in there already. What I'm going to do is to go through every single question from the top. And bear in mind, our marketing department has got a very special promotion for only the people who joined us at this webinar. At the end of the Q&A session, Andre would come online and quickly explain to you how it works. Bear in mind, only the people who joined the webinar actually qualify for this, so because he already has a list. Now, let's deal with the questions, and before we bring Andre to go through the special offer for you. Now, I can provide, let's go. Right, now, first question I got here, for bulk resistivity with the Resipod, does the device work for all cylinder sizes, diameters, and lengths?
We do have an upper limit because the width of the size of the plates. We can accommodate samples up to 150 mm. In principle, there is no limit, no lower limit. Well, I may just say that it is normal for cylinders to be tested for 150, 180 millimeters. I don't have any direct experience on micro cores, meaning 28, 1 inch core. But in principle, the correction factor is very simple. You just input the size of the plate and the height of the core. So no limits, no lower limits.
Yes, thank you. I've got a question here. What actually happens if you do the surface resistivity test over rebars, and what kind of reading will show up on the screen?
Well, there is no specific warning. What will happen is that an apparently low resistivity appear because electrical current will flow through the rebar. So this is something that only a rebar locator can avoid.
And hence we highlighted and emphasized the fact that before you start doing your surface resistivity, you need to locate your rebars and find out about your cover. Next.
I think we might have skipped a good one, which I'll go by myself. Does the surface resistivity test use AC or DC, and what are the typical electrical parameters involved? We're working with a typically highly resistive material, so direct current won't be able to do that unless you use huge potential, which you don't want to do with your hand. So we use, our instrument is 40 Hertz alternate current. We impose a current which, depending on the two ranges available, we force 200 microamperes or 50 microamperes. Those are the parameters fixed on the instrument.
Brilliant, thank you. By measuring resistivity and half cell, obviously together, is it possible to calculate the corrosion rate?
There's no such thing as a direct exact calculation, but you can estimate according to literature and comparison.
Exactly. I mean, the numbers that we showed you on the screen, I can go back to that slide, for example, here. And we highlighted it. These numbers are recommendations based on the literatures that some of them we highlighted again on the Tuesday's presentation. Please refer back to them, the recording of that. And then we took the number from the sort of our on-site testing that Guido just went outside and did and quickly came back in, and then use that as a reference. By measuring resistivity and offset, okay. Now, would a temperature much lower than 68 degrees Fahrenheit, which again we're looking at about 20 degrees Celsius,
that's the standard
increase the resistivity readings, and would it be at the same rate as an increase in temperature 3% degree for saturated?
Okay, those 3% per degree, it is linear for reasonable variation. The point is that there is no actual modeling of the variation of resistivity over huge temperature intervals. The key point is that we don't really need that, because it will always be a qualitative comparative test that we do on one specific day or one specific week over the structure. So all the different areas of the structure will be evidence whatsoever. They might be shifted up or down, but hey, just keep track of the temperature.
Yeah, exactly. So these are obviously an indication. Next question. Is there an effective temperature range for using electrical resistivity? Again,
no, there is not.
No. The relationship between resistivity and potential again.
Well, just let's go very shortly on that slide. In principle, there is no relationship whatsoever between half cell potential and resistivity. Half cell potential is telling us the steel. Is the steel passivated? Is it corroding? Yes, no. Resistivity is saying how good is the concrete in protecting the steel. Now, what statistically is bound to happen is that low resistivity area are more likely to have a corrosion. So statistically speaking, they will be accompanied by very negative potential. On the contrary, statistically speaking, high resistivity area are more unlikely to promote corrosion. Hence, we will have less chances of seeing very negative potential. But we have to look at them together. We're not trying to model anything here. We're just looking at facts and assigning different risk at different area. Negative potential, low resistivity, risk, high resistivity, low potential, nothing is happening, and probably nothing will happen in the next future. Passive potential is saying, hey, concrete, the steel is there, nothing is happening there. We have no electrochemical reaction, but if we see that being accompanied by a low resistivity value, then we will state a potential risk for the near future for the structure.
Brilliant.
Again, no physical correlation, just a statistical correlation that we have to keep in mind.
You know, I knew you're passionate about concrete, but not this much. Right. Okay. Now, how corrosion rate or corrosion likelihood can be predicted based upon half-cell potential data?
Well, there will sure be a dedicated webinar for it, but let's say that we're not speaking about corrosion rate with half-cell potential. The mapping of the half-cell potential values, and even more than the values in themselves, the gradients and the shape of the variation is the tool that we use to verify and to find active hotspot. I'll be more than happy to keep on the discussion, but half-cell potential in itself deserves probably a whole time that we don't have here.
Great. Okay, next questions I've got here is how much does the surface resistivity device cost? A lot of money. That I don't know. We can definitely let you know. Is there an office in Southern USA? We do have 2 offices in USA. I would like to include surface resistivity in my research and
that will probably definitely forward to
absolutely. We will forward your request to our US office, and stay tuned because our head of marketing would be announcing a very special offer just for the people who attended this webinar. Now, I've got another question here. Can we estimate the corrosion rate forward resistivity after the application of a hydrophobic impregnation or a corrosion inhibitor application as any evaluation of a repair protection method?
Absolutely yes, but that should be anyway accompanied by half-cell potential. Again, we want to see how the steel is, half-cell potential, and how the concrete is repaired, impregnated, impermeabilized, resistivity. That's for sure.
Thank you. Now, I feel this system is similar to Geoelectric's laboratory tester, same like Miller box production. Can we use of Miller box production for this test? I feel that, so are you familiar with this particular?
I apologize, I am not.
Okay. Mr. Mujtaba Ahmadi, could you please send us an email, webinar@prosec.com, with a little bit more detail about the instrument in question. Myself and Guido will personally look into it, and we'll get back to you with a clear sort of answer to your question. We are not 100% familiar with the instruments that you're referring to here. Second question. Is ASTM G57 for 4 electrode test? There is existence a temperature corrective chart. Is it in existence same like the chart for solid in this test for concrete? Do we have a chart?
Okay, now that's a tough one. I know we have it in literature.
Just to let you know, these questions are coming from Iran. Generally, they come with tough questions.
My God. No. Again, I know for sure, and I can provide probably some reference based on literature. Just I'm not sure we have some correction factors for charts for on-site testing, as mainly the charts provided in the most evoluted standards are for lab testing, and they have solved the problem by stating, hey, you work at 68 Fahrenheit or 20 Celsius.
But again, what we can do, Mr. Ahmadi, please send us an email. Again, highlight these two little questions. We've got track of them here anyway. And we will look into it, and we will gladly get back to you with the answers. Now, what influence does cracking on the surface of the concrete have on resistivity measurements?
Well, it gives apparent high values. So resistivity is not an established method for cracking investigation. It is affected by cracking, and you don't want to measure over cracks. As far as I know, there is no systematic experimental work for estimating crack depth with resistivity.
Mm-hmm. Thank you. Now, I've got another question here. Do you have any instrument wherein rebar and corrosion analysis are integrated in one instrument? Simple answer to that is no. But we do have instruments to take care of these individual applications.
Sure.
Either can actually
it might be my
down.
boss writing that thing.
Okay.
The answer is not yet.
Okay. Good. All right. We actually have another question here. Guido, could you please...
Sure, just coming. By using the variable spacing probe Resipod, Resipod geometric, we can vary the depth of the measuring point? Yes. Just like in geophysics, the broader the spacing, the deeper the range of it. This can provide some information about, this might become useful when dealing with highly carbonated concretes. Without going into detail, carbonation increases resistivity, and so the fact that you might observe a decrease in resistivity with a broader spacing might give you an idea of the carbonation being there.
Brilliant, thank you. Again, our last call for questions. Is there anyone else that has any particular questions that would like to ask us?
Hey, by the way, I believe that even if they're not in real time, I hope that further questions that might come in the future just get through, and
yes,
we are there
absolutely.
to provide what we can provide.
Yeah, please note our technical webinar email address, webinar@prosec.com. Any questions that you have, any concerns, and perhaps a particular application you would like us to cover, we are open to suggestions. There's going to be a little survey at the end when this thing finishes as well. Please give us your feedback, and if they have any recommendation, and we will keep you up to date with all of our upcoming webinars. And on that note, once again, thank you for joining us. We had a blast with these 4 sessions that we conducted Tuesday and today. And we would like to hopefully see you for the future webinars that we will do. And on that note, thank you. Goodbye from me.
And thank everybody for your time and your patience. And thanks, Ali, for the great work that made this possible.
Lastly, I would like to also thank both Andre and Serena, which again work really hard in the background, making sure that our sessions go smooth, and they for sure did. See you at our next webinar. Bye-bye.